Hello and welcome to the Interjection to Magnetism. So this lesson's a review, overview of the 3U course. Actually, the next two you're going to find they're going to go pretty quick. And I'm not going to spend a whole lot of time here because this is from the 3U course. I do go through it again for those that haven't done the 3U in a while, but it gives you a feel for what you're expected or what you need for this particular end of the unit here. So the goal is I can successfully explain the concepts discussed in 3U. So as we go through here, magnets. Naturally occurring magnets are known as lodestone. So those are ores that we find in the Earth's surface. Magnetic fields. So a magnetic field is the field that surrounds a source. So if we have, let's go with a bar magnet, that is our source. We have our north and south. The field lines outside the magnet, north to south, and then there are parallel lines inside the magnet that connect to those loops. All right, so there is your magnetic fields. Very similar rules to electric fields and gravitational field lines. And we have a force of attraction or repulsion caused by the dipoles on the magnet, and that's the north and south. Two defining characteristics. Magnetic fields occur naturally in substances that have magnetic character or internal makeup. And that's typically only the ores that are involved there. And secondly, can affect not only other magnetic substances, but also electric charges. So magnetic fields have an influence on the electrical concepts that we were discussing, and we're going to see that in the next day's note. So when you print this off, it already had the majority of the note from previous year. Again, I'm not going to have you copy out something that's in your 3U notes. So magnetic character, it's related to the condition of the atoms in the material, and we really don't understand it. And I talked to quite a few people about this in the grade 11 course. It remains a theory because we have no real proof to support this particular concept. So basically what the theory is that all large magnets are made up of many magnetic regions, which we call domains. The magnetic character of the domains comes from the presence of even smaller units called our dipoles. And down here in the diagram, a dipole is, I draw it as a smaller bar magnet within a material. So dipoles are called north and south by convention, and when the dipoles interact with their neighboring dipole, and when they align themselves, then we end up with a larger magnetic domain. So they kind of get together, get the job done, and create a magnetic substance. Okay, so the diagram here illustrates how each of these, they're randomly arranged, the dipoles or the domains, and then all of a sudden they line up into kind of a matrix format here. And it kind of, I guess you can think of it in terms of it amplifies each dipole's magnetic field or each domain's magnetic field strength. And when they align, they create a large magnetic substance. So that is your domain theory. So materials that allow for dipoles to be aligned, they create a larger magnetic character. We have our nickel, our iron, our cobalt, our copper, those types of material have a greater magnetic character. So the law of magnetic forces, again, that hasn't changed in the last month or so since you've been within the grade 11 course. Similar magnetic poles repel. So north-north would repel, south-south would repel, and dissimilar ones attract. So north-south will attract. So magnetic phenomena. Magnetic induction, we talked about that, and that's when ferromagnetic materials can be magnetized. So first of all, they have that magnetic character that allows them to become magnetized, and typically they may be non-magnetic to start with, and then we can create or force them to become magnetic. Then we have permanent and temporary magnetism. So looking at the second point here, some materials demagnetize easily, others maintain their magnetic domains for a long time. So, for example, that junkyard magnet or the electric bell, those are examples that they demagnetize easily and don't hold their magnetic field for long periods of time. You wanted something to be short-lived. Reverse magnetism. That is the concept where we have a magnetic material here. It is overall north-south. So we have this end is really the north. That's the south end. We bring in a stronger magnet, and what happens is it makes the domains flip around. So now we have the south end down here and the north here. So that happens when a stronger magnet, it influences the magnetic field for the weaker magnet. If we break a large magnet into pieces, something you don't have to worry about, you don't lose the magnet. We break it into chunks. We now have two smaller magnets with the north and south poles forming up. And finally, maximum strength. There is a limit to how strong a magnet can be, and we're going to talk about some of the characteristics here as to, or limiting factors, I should say. So sketching the magnetic field, it's done here for you in the diagram. We have the number of field lines drawn proportional to the strength of the field. So if I wanted to draw an equivalent weaker magnet, so I'm not going to do it same scale size here, north to south. So I'm looking at that one. If I count the number of blue lines here, so let me get a red out here. So we got 1, 2, 3, 4, 5, 6. So I've drawn that one with 6 lines. I want this one to be significantly weaker. So I'm only going to draw 2 field lines through it, which would mean I'd have one going in either direction. So this would represent a significantly weaker magnet. All right. And then thus this would represent a much stronger magnet because it depends on number of field lines, okay, as mentioned up there. So if you want to represent a very, very strong magnet, you would draw many, many field lines. And the directions of fields is defined by the direction of the North Pole. So our convention, the field lines go from north to south outside the magnet. Inside the magnet, it is traveling south to north, and we got a continuous kind of circular cycle going there with our magnetic field. Now you will notice I have the magnetic force here. If we were to put a magnetic particle in there, and typically I'm going to create a magnetic particle, or sorry, a material that's an object that's influenced by a magnet. Oops, let's group that together. So here is my piece of my metal filing. So this metal filing, if I was to place the magnetic filing here, the force acting on it is tangential to that curve. So the magnetic force acting on it, it makes it want to move in that direction. If I was to put the filing right here, the tangential force would be facing in that direction. Magnetic force. So it gives you the direction that if this particle, if the magnetic field was strong enough, it's the direction the particle would be sent. Okay, similarly here, magnetic force, tangential. So that tangential line tells you the direction the object would like to move, if possible, within that magnetic field. And we see evidence of that. If you recall the demo that we did in the grade 11 course, I'm just going to extend it down. So if this was, I'm going to do a side view, just to refresh your memory. Remember that we put the magnet underneath the piece of paper, so I'm looking at the side view. Here's that piece of paper. And remember the iron filings tried to stand up at the edges? And that's because the magnetic field is in 3 dimensions. So it is forcing that iron filing in the direction tangential to the field. And then people, if you were to help remember, I had a bunch of good questions. Well, does the magnetic field extend down underneath the desk? And absolutely. It's just as it passes through the desk, the strength of the magnet, the field strength would be a lot less. So we couldn't exactly put stuff underneath the desk because it's just not strong enough. But that's why those iron filings were standing on edge. It's because they were moving in the direction of this magnetic force vector. All right, so they are coming out of the page. So that's why they're standing up. It's that force is causing them to stand up within that field. All right. So why are magnetic fields important? So what I have here is I have the Earth sketched out here. And I'm not sure it's part of, well, it should be part of it since this is the one I printed off from. So if this is my Earth, we have a magnetic core inside the Earth. So we have magnetic field lines traveling south to north within the planet. And then outside the planet, we have these field lines. So the field lines are circular like this, or shaped in that fashion. So they do move in that direction. So from electricity, the Earth can be positive or negative or neutral. Okay, we know that when we did back in grade 9 or 10 when you did that. The Earth's core is a liquid metal, and the molten core is moving due to convection. So that motion is the combination of electrical and magnetic characteristics that sort of create that magnetic field around the Earth, surrounding the Earth. So, and again, this is why your compass will point to magnetic north for you when you're out orienteering or finding your way through the wilderness. All right, so very, very important, and we influence it every day. You can see that because we're on Earth, we are within the Earth's magnetic field, so we're already experiencing or influenced by it. And that's it. That is the extent. It must be, the homework must be on the previous page here somewhere, or not at all. So the homework itself, if I recall, your homework is not at all. This is just a straight out review of some of the grade 11 concepts we talked about. So you're able to either continue along your way if you need work to do. If you have work you're still working on, then it allows you to kind of continue on that tomorrow. So anyhow, we will see you tomorrow. And for some that are moving along, we'll see you in the next video.